A relic from beyond 7 billion years in the making tore into the solar neighborhood. And that is our next story, which explains how the celestial visitor, known only as 31 Atlas, has rewritten the physics textbook.
A huge update on our favorite interstellar object. It could be the biggest update in the solar system.
Astronomers tracked an interstellar object called 3I Atlas as it passed through our solar system, and the data proves this cannot be a normal comet.
You were saying that when it went behind the sun, the natural explanation for the non-gravitational acceleration in the thrust might be because it burned off a bunch of chemicals or something, and that was giving it the thrust to the tune of like 13%, and we would see a humongous tail maybe. What is going on?
We see other comets in the solar system that have a beautiful tail away from the sun. Behind them, Lemon is an excellent example.
The object fired jets straight at the sun while spinning every 16 hours. Yet those jets stayed locked in place instead of smearing across space like they should. Its chemical makeup shows industrial-grade nickel with almost no water. And when it accelerated near the sun, the body stayed intact instead of breaking apart like ice. But can a frozen comet really produce steady jets that ignore physics and solar wind? And what happens if 3I, Atlas, is actually technology designed to look like a comet? The impossible path that looked planned. 3I, Atlas, entered our solar system on a path that should make any astronomer uncomfortable. The object travels on a retrograde orbit, meaning it moves opposite to the direction planets orbit the Sun. That retrograde trajectory aligns within 5 degrees of the ecliptic plane where major planets travel. The likelihood of a random interstellar object arriving on this specific alignment sits at 0.2%. That's 2 in 1,000. Not impossible, but definitely raising eyebrows. The timing makes it worse. 3I, Atlas arrived at precisely the right moment to pass within tens of millions of kilometers of Mars, Venus, and Jupiter. 2 of those planets sit in the habitable zone where liquid water can exist. Jupiter hosts moons like Europa and Ganymede, with subsurface oceans that might harbor life. A random visitor would need extraordinary timing to sample multiple potentially habitable targets in one pass. Think about it this way. If you threw a rock from another star system toward our solar system without aiming, what are the chances it would arrive on the exact plane where all the interesting planets live at the exact time to visit 3 of them? The math says that happens 5 times out of a million tries. Those aren't good odds for randomness. The perihelion timing adds another suspicious detail. When 3I Atlas reached its closest approach to the Sun on October the 29th, 2025, it positioned itself exactly opposite Earth's location. From our perspective, the object disappeared behind the Sun's glare during the period when it changed velocity and direction. Astronomers lost visual contact during the most important phase of the journey. The one time something interesting happened, we couldn't see it. ESA's ExoMars Trace Gas Orbiter managed to observe 3I Atlas from Mars orbit. During this hidden period, their data showed the object changed velocity in ways that sunlight pressure and normal gas release cannot fully explain. The speed change happened precisely when Earth-based telescopes couldn't track it, as if someone knew where our blind spot would be and picked that moment to adjust course. NASA's Atlas Survey Telescope in Chile first spotted the object on July 1st. 2025. Within hours, astronomers knew something was off. The object wasn't following a normal curved orbit around the Sun. It was traveling on a hyperbolic trajectory, meaning the path looks almost perfectly straight. The orbital eccentricity measured 6.139, the highest ever recorded for any solar system visitor. That extreme number means the object is moving fast enough to escape our solar system entirely without slowing down. The speed backs up that claim. 3E Atlas entered traveling at 58 kilometers per second relative to the Sun. That's 130,000 miles per hour, nearly double the speed of Oumuamua, the first confirmed interstellar object discovered in 2017. when the object reached its closest approach on October the 29th. Gravity had accelerated it to 153,000 miles per hour. No object born in our solar system moves that fast unless something launched it deliberately. The arrival direction adds another layer. 3I Atlas came from the direction of Sagittarius, near the Milky Way's galactic center. The path brought it close to Mars on October the 3rd, then swung behind the Sun, where Earth-based telescopes lost track. During the most critical phase, Mars was 29 million kilometers away during the pass. That's close enough for detailed observations, but far enough to avoid gravitational disruption that would mess up the approach to the Sun. Pre-discovery images from the Zwicky Transient Facility show the object was active as far back as May 21st, 2025, when it was still beyond Jupiter's orbit. Normal comets don't start releasing gas until they get much closer to the Sun, where heat can turn surface ice into vapor. 3I Atlas began producing a visible cloud at roughly 9 astronomical units from the Sun, exactly where carbon dioxide ice starts to turn into gas. That timing is precise, almost engineered, as if the object knew exactly when to start shedding material to look like a comet. Experts who study orbital mechanics are uncomfortable with these coincidences. The path looks less like random debris drifting through space and more like someone calculated approach windows to visit multiple planets while staying hidden during course corrections. When you stack a backwards orbit with perfect planetary timing and a hidden velocity change, the pile of coincidences starts to lean towards something planned. But promises are easy to make about trajectories when you haven't examined the chemical signature that separates 3I Atlas from every comet in our records. The chemical makeup that doesn't make sense. Spectroscopic analysis revealed a makeup that makes veteran astronomers nervous and materials engineers raise eyebrows. 3I Atlas shows unusually high nickel concentrations with a nickel-to-iron ratio that matches factory-made alloys rather than natural space rocks. The nickel-to-cyanide ratio sits orders of magnitude higher than any known comet, including 2I Borisov, the only other confirmed interstellar comet on record. The water problem tells an equally disturbing story. Normal comets are basically dirty snowballs where water ice makes up most of the mass and drives gas release through solar heating. 3I Atlas contains only 4% water by mass. That's not how comets work. Carbon dioxide and carbon monoxide appear to be the main gases, which can turn into vapor farther from the Sun than water, but don't have enough energy to explain the observed brightness and massive cloud without burning through material at impossible rates. To put this in perspective, imagine finding a car that runs on orange juice instead of gasoline. Sure, liquids can power engines, but orange juice doesn't have the energy density to make a car go fast or far. That's what we're seeing with 3I Atlas. The fuel mix is wrong for the performance we're observing. The nickel concentration specifically echoes industrial chemistry that engineers use to make pure nickel coatings. The process requires precise temperature and pressure conditions that don't naturally happen in comet birth regions. Labs have spent decades refining nickel carbonyl cycles for building heat shields and high-temperature engine parts. Nobody's claiming 3I. Atlas is running a metal factory, but the chemical fingerprints match controlled industrial processes rather than random freezing and thawing in deep space. Polarization measurements add another troubling dimension. Light reflecting off 3. Ice Atlas shows curves that indicate compact, smooth surfaces rather than the fluffy, porous textures typical of comet nuclei. Smooth surfaces with low porosity scatter light differently and retain heat differently, which fundamentally changes how jets form and how material escapes. If the surface isn't fluffy ice mixed with dust, what is it? And why does it behave like engineered thermal protection rather than natural cryogenic slush? Near perihelion, 3I Atlas brightened faster than any known comet and showed a color bluer than the Sun itself. That blue tint suggests smaller particles and different surface materials reflecting light in ways rarely seen. The brightening speed outpaced models based on standard comet chemistry and solar heating alone. Something about how this object releases material and reflects light doesn't match the comet playbook. What makes all of this truly alarming is how it connects to the next discovery. The jets don't just look wrong chemically, they behave in ways that physics says shouldn't be possible. The jets that broke every rule. Images from multiple observatories captured narrow jets pointing directly toward the sun, extending over 950,000 kilometers while staying in tight columns. 3i Atlas rotates with a period of 16.16 hours, which means any surface opening should sweep through day and night cycles like water spraying from a spinning sprinkler. That rotation should create a spiral pattern with clear pulses or beads spaced out in a predictable way. The expected pattern never showed up. Observations from November the 9th, 2025, by astronomers Nebling and Borner showed tightly focused jets stretching beyond 1 million kilometers. At the normal speed that gas moves when it evaporates from a comet at 400 meters per second, material takes about a month to cross that distance. How do jets keep their aim without getting disrupted if the core rotates every 16 hours? The math doesn't work. Let's break down why this is so strange. Imagine you're spinning around once every 16 hours while holding a garden hose that shoots water at a steady speed. The water coming out would create a spiral pattern in the air because you're rotating while the water travels outward. Now imagine that water somehow stayed in a perfectly straight line even though you're spinning. That's what 3i Atlas is doing, and it breaks the basic physics of rotating objects releasing material. The Hubble Space Telescope captured detailed images on July the 21st, 2025, showing 3i Atlas's teardrop-shaped cloud with remarkable clarity. The symmetry and focus of the released material doesn't look like chaotic gas escaping from a tumbling ice ball. It looks like directed flow from a nozzle designed to keep thrust pointed in one direction. Engineers who work on spacecraft engines recognize the fingerprint. Steady exhaust with minimal spreading, typical of directed mass flow rather than random venting from heating. The only explanation that fits observed data without piling on special conditions is that jets keep their direction through active control. A rotating frame or cage structure could hold nozzles in fixed positions while the core spins inside, similar to how spacecraft use gyroscopes to maintain pointing while internal parts move. That picture is simple, but it matches observations that refuse to fit passive ice models. No exotic thermal geography needed, no special shadowing required. Just active stabilization doing what active stabilization does. Experts who study rocket propulsion are uncomfortable with claims that natural gas release can produce focused thrust across million-kilometer distances while ignoring 16-hour rotation and 1,000-watt radiation pressure. The math works for directed systems with nozzles built to maintain thrust direction. The math breaks down for porous ice where vents fire in multiple directions, and solar wind tears apart any forward-facing stream within the first few thousand kilometers. When you have to add 5 special conditions to make the natural explanation work, maybe it's time to test whether the simple explanation fits better. But there's one final piece of evidence that separates speculation from physics, and it happened precisely when Earth couldn't watch. The hidden burn that changed everything. Tracking data revealed speed changes that orbit prediction software couldn't ignore. 3i Atlas deviated from a pure gravity-driven path by amounts that require extra forces beyond the sun's pull. If that push came from normal comet gas release, mass loss would need to reach at least 13% of total mass. That fraction usually tears apart fragile cores or leaves clear signs of breakup, tumbling, and debris, trails spreading through space. No breakup happened. 3. Atlas came through perihelion intact with no fragment clouds, no chaotic spin changes, no debris field. The acceleration occurred mainly during the period when the object was behind the Sun from Earth's view, hidden in glare where tracking becomes impossible. Once it passed perihelion and returned to where we could see it, the path settled into a clean line as if a controlled burn had finished, and the craft went back to cruise mode. The speed change exceeded any natural comet ever observed except for sungrazers that pass within a few solar radii, where they absorb 1,000 times more heat than 3I Atlas got at its closest distance of 203 million kilometers. The tracking residuals plotted over time show a pattern that looks like brief, steady thrust, followed by coasting, not the noisy, chaotic fingerprint of random vents firing at different angles as solar lighting changes throughout rotation. Here's what makes this truly suspicious. ESA's data from the ExoMars Trace Gas Orbiter improved path predictions by a factor of 10 compared to Earth-based observations. The 10 times accuracy boost came from triangulation using Mars-based measurements that gave different viewing angles. The better orbit data made the non-gravity acceleration even more obvious because it removed measurement errors that could have masked the effect. With cleaner data, the velocity change stands out like a sore thumb. The body staying together after perihelion becomes the smoking gun. Porous snowballs that lose more than 10% of mass quickly tend to shed pieces, grow new active spots, or start tumbling as uneven mass loss creates twisting forces. 3I Atlas kept its structure solid and went back to a smooth path, as if whatever provided the speed boost was built to do exactly that without damaging the platform. Ice doesn't behave that way when it loses that much mass that fast. Classic comets can produce similar effects when they skim extremely close to the Sun, where heat stress becomes extreme. Interior ices cook and explode, shapes warp, and paths twitch chaotically. But 3Y Atlas didn't dive that deep. Its closest approach kept it well outside the region where solar heating becomes a hammer. The energy math doesn't balance. The sunlight it received can't pay for the observed push without burning through a painful chunk of total mass, yet the body shows no signs of that level of mass loss in observations after perihelion. The structure looks the same. The rotation stays steady. No debris trail appears. It's like watching a car accelerate hard without using any fuel. The final damning detail is path precision after the event. Once past closest approach, 3I Atlas went back to a trajectory that matched predictions from before perihelion, as if guidance systems had run a planned maneuver and then shut down to return to cruise. Natural gas release creates messy paths with ongoing velocity changes as different surface areas heat up and vent unpredictably throughout rotation. 3I Atlas acted like a spacecraft that fired thrusters during a calculated window and then turned them off. Clean start, clean stop. Clean return to predicted course. Experts who study spacecraft maneuvers recognize the pattern. When you plot the difference between predicted and actual positions over time for a spacecraft doing a burn, you get a signature that shows steady acceleration during the burn, followed by return to ballistic flight afterward. 3I Atlas shows that exact signature. When you plot the same data for a natural comet releasing gas randomly, you get noise that varies in strength and direction as the comet tumbles and different vents turn on and off. 3I Atlas doesn't show that noise. It shows a pattern that matches deliberate thrust. The timing of the burn location matters too. It happened behind the Sun, where Earth couldn't watch. If you wanted to adjust your path through the solar system without being observed by the one planet with advanced telescopes, you'd time your burn for exactly that location. The fact that the biggest velocity change happened in Earth's blind spot while a Mars orbiter caught glimpses from a different angle reads less like coincidence and more like someone knew where our observation gaps were and used them outro. 12 separate anomalies stack into a case that refuses conventional explanations. A trajectory aligned to the ecliptic with punctual planetary encounters and hidden perihelion timing. Chemical composition matching industrial nickel alloys with almost no water, million-kilometer jets that ignore 16-hour rotation and 1,000-watt solar wind pressure, non-gravitational acceleration during Earth's blind spot, followed by intact structure and resumed trajectory. Each anomaly can be stretched to fit natural models if you add enough epicycles. Exotic thermal geography that doesn't pulse. Unusual chemistry that mimics industrial processes. Structural integrity that defies typical comet fragility. Jets that forget rotation physics. Stack them together, and the natural explanation requires more patches than the alternative. Skeptics demand extraordinary evidence for extraordinary claims, which is reasonable. But what counts as extraordinary when 12 separate observations all point the same direction? What counts as skepticism when critics wave away anomalies by citing comets that operate at different distances with different rotation periods under different radiation pressure? The next interstellar visitors will provide the real test. NASA's ATLAS system and the Vera Rubin Observatory will spot dozens of interstellar objects over the coming decade. If 3Y. Atlas is a one-off outlier. The signal fades into history as nature's occasional weird trick. If directed interstellar probes traverse our neighborhood, future surveys should detect more objects with similar characteristics. The question isn't whether we prefer natural stories or built ones. The question is whether we're prepared to catch the truth at full speed when the sky gives us another chance. 3I. Atlas challenges habits more than laws because gravity still rules and sunlight still drives chemistry. But the order and timing and composition and jets and thrust together tell a story that doesn't sit well in the old chair. What do you think? Is 3I Atlas the most unusual comet ever observed? Or is it something we've never encountered before? Drop your thoughts in the comments below, and if you want updates when the next interstellar visitor crosses our sky, make sure to subscribe.